Hey guys, hope everybody had a good weekend and spent all your free time thinking about perturbation theory and scattering theory and all that good stuff. I know I did. Uh, so last time we left off, we had started talking about scattering theory, and so I thought I would. It's kind of a long weekend for me. I don't know about you guys, so I thought I'd start out with just a little refresher to remind us where we are. So the basic setup is this picture that I have here, okay? And so the types of experiments we're considering are typically called fixed target experiments, because one of the uh, particles or whatever that's interacting is stationary while the other's in a beam, right? So we have some type of accelerator or some, and we're shooting these particles off, and we assume that we can control the initial energy and the momentum, or at least we know what they are, to a certain degree. Typically, the dimensions of the target, or really not the target itself, but the potential that these particles are going to interact with, is a lot smaller than, say, the cross sectional area of this beam. And that allows us to make a handful of approximations that make life easy on us. But the main question we're trying to answer in scattering theory is, given this setup, what's the probability that if we put a detector at some angle, call it theta, off of the beam axis, what's the probability that we're going to get particles scattered into this detector, right? Because if the target was there, the probability would be zero. But because of the target, there's going to be some deflections depending on the potential, and we should see particles showing up in our detector, and that's what we're after, is try to compute the cross section or the probability. So we work with so our main thing that we try to compute in scattering theory is the cross section, or the differential cross section. And typically, it's just basically the number of scattered particles that we get in our detector per second, divided by the number of incident particles, right? So the particles, that's a number that we know, because we can basically, we have an idea of the number of particles in our beam. And so what we really need to compute is the scattering, the amplitude, or the probability that the particles scatter. But we know this denominator is basically what I'm trying to get at. Okay, so that's our setup, and typically what we do is we start by writing down the wave function, and we assume that the incident wave function is a plane wave, right? We can approximate it as a plane wave because of the smallness of the scattering potential compared to these distances where our gun is, or where our detector is. You can basically treat these particles as a plane wave. And then the scattered wave, so the total wave function is made up of the incident wave and the scattered wave. And it's the form of this, the form of the wave function is going to depend on the form of the scattering potential, okay, as we'll see later on. Right. So we are working in 3 dimensions, right? And anytime we have a setup like this, we want to try to make use of any symmetries that we might have. And in this case, and all the cases that we'll consider, we'll always have spherical symmetry. So what we want to do is work in spherical coordinates. And so we want to write down the scattered plane wave, general wave function in 3 dimensions. And note that we're very far away. This detector is relatively, it's very far away from the potential, and so what we can do is basically write down the wave function for a free particle, and that's the meaning of this r goes to infinity limit. Yeah, and then we found last time that these coefficients AL and BL, they're not independent, and they actually obey this this relationship. And so what we can do is reduce this nasty looking thing down to something that looks a little more manageable. So we have the radial piece, right? And so the E, the IKR over R. So this is a spherical wave. It's outgoing, outgoing spherical wave. And then all the angular stuff, the stuff that's inside these Neumann and Bessel functions, that's all captured in this thing that we call the scattering amplitude, right? So all the angular dependence is in there, and we have a radial piece. Okay. And I think last time we showed that just by using basically your physical intuition, you can find the relationship between the cross section and the scattering amplitude, and it's just based. So the cross section is just this scattering amplitude modulus squared. Okay, so this is one of the main results from last time, and you'll see it a lot more. So finally, last time we ended with a nice little calculation that ends with what's called Fermi's golden rule, and it basically gives you kind of a quick and dirty, or just nice, a good approximation to scattering rates or transition rates. Right, that's what this symbol means here, and it basically boils down to just the matrix element of the perturbation Hamiltonian modulus squared, and then some factors, and then a Dirac delta function basically enforces energy conservation. Okay, so we're going to make use of this today. All right. So what we want to do, like I said last time, so the cross section, we have a formula for it. And now all the work that we need to do we have to try to figure out how to compute this scattering amplitude. Okay, and that's where perturbation theory is going to come in. So the first thing we want to do is talk about something called the Born approximation, and this is basically the case where you compute this guy to lowest order in your scattering potential. Okay, so what we're going to do is, again, consider our initial beam or particles as wave packets, right? And again, there's, these wave packets, their dimensions compared to the target are big, right? So we can approximate them as a plane wave. And what we want to do is, it turns out to be more convenient to work in momentum space when we're doing these calculations. And that's something that if you go on and take quantum field theory, you'll see that you almost always work in momentum space. Things are a lot easier to compute, and then at the end of the calculation, you just take a Fourier transform to get back to position space. So this has a couple of advantages. So, like I said, it's nice because it simplifies a lot of the calculation, but it's also nice because we can control. If we work with momentum eigenstates, then we know what the momentum is, right? When we fire, the particles out of the gun or the accelerator or whatever, we know what the momentum and energy is, right? So that gives us a handle on at least something in the problem, right? We know what the initial state is. So we have a time dependent problem here, right? So we want to ask, if we set the initial state to this momentum ket, how does this state evolve with time, right? And we all know since last semester that the time evolution of these states is given by the propagator, right? The time evolution operator. Okay, and this is just a simple form, so we're assuming that the Hamiltonian doesn't have any time dependence here. Okay, so all the time dependence is just captured inside this exponential. Again, we can make use of the fact that the interaction time, so the time that the particle on the beam interacts with the particle on the target, because the time is so short, we can actually take the limit where the initial time goes to we take that to minus infinity. The final time we take to plus infinity. And when we take the limit of this thing, take those two limits, we end up with a new operator. And this operator is denoted by S, and it's somebody gave it the name, the S matrix. But it's basically just, it's defined as the propagator. So we define our initial state, and then we propagate it using the time evolution operator. But if we take the limit, if we take these limits of this guy, that gives us what's called the S matrix. Okay, and the S matrix is one of the fundamental quantities, or one of the fundamental things that you're always after, that you want to compute when you're doing scattering theory. So I should say that, so we're talking about scattering, right? So the scattering is going to be because of whatever potential there is between the particles, and that potential is inside of this Hamiltonian, right? So the S matrix is going to depend on the scattering potential through that dependence. Right. Okay. So the particles are our initial plane wave is going to come in, interact with the external potential, and it's going to be scattered, right? And so what we're after is, what's the probability that we detect particles in a particular direction, and our detector has some opening angle in this in the spherical, or the angular coordinates. Okay, so that's what we want to compute the probability, but we're working in momentum space, right? And if we want to compute that thing, if we want to compute that probability, it's basically just the probability that our final momentum, right, lies in a cone of that opening angle, right, in the direction, right? So in other words, if we go back to this picture, so we want to compute the probability that we'll have some particle that has momentum that's pointing into this detector, right, that hits some part of this detector. Okay, and we can compute that in terms of our S matrix using this formula. So this is the probability that we have a particle with momentum P1 going into our detector, right? And so again, this is our matrix element, our S matrix, I guess we would call it, and this thing is going to be modulus squared, right? So we're computing a probability, and so what we have are we wouldn't just have one, only one momentum. So we basically sum over all the momenta vectors that enter that detector. Okay. And so what we do, this thing, to try to compute it exactly would be impossible, basically. So what we do is we can use an approximation, and we'll use perturbation theory. Okay. So we're going to assume that the scattering potential is small, right, compared to the simple piece of the Hamiltonian, and use perturbation theory to try to compute the S matrix. Okay, so this is where Fermi's golden rule is going to come in handy. So we're going to use Fermi's golden rule, but we're dealing with momentum, right? And momentum don't come in just discrete quantities. Momentum is a continuous quantity. So we have to make the replacement of that sum that we had in the above expression. We have to replace it with an integral, right, where I'm integrating from 0 to infinity. Okay, so again, momentum has 3 dimensions. 2 of them are locked up in this solid angle, and the radial piece, if you will, is here, and this is the thing we're integrating from 0 to infinity. Okay. All right. So what we want is, if we want to use Fermi's golden rule, we're interested in computing the rate, right? The rate that particles that started out in pi are going to end up in our detector, right? And the rate is just it's the rate of change of the probability. Okay. So what we would have is just the derivative of this thing up here, okay, the time derivative. Right. So here, what are we doing here? Okay, so here we're using Fermi's golden rule. All right, so I'm replacing. I'm just basically plugging in the expression that we arrived at last time for Fermi's rule. And so what we need to evaluate is this matrix element, right? Let's see, we're integrating. Oh, so we want to perform this integral, and luckily we have this delta function here that we can use to do the integral over the p final. And when I do that, I'm left with just this nice little simple line here. Okay. And here we're assuming that that PF and PI have the same magnitude, which would make sense. You wouldn't expect these particles to the initial and final method to change dramatically or drastically, right? Okay, so we've got our rate, right? The rate that particles are scattered into our detector using Fermi's golden rule. And we know that if we want to compute the cross-section, we need to know not only that rate, but we also need to know the incoming probability, right? And now we're dealing in momentum space, so we've had to use the Fourier transform to write this incident current in momentum space, right? And when I do that, I pick up this factor of 1 over 2 pi h bar cubed, but it's a simple transformation. Okay, so we've got the rate, and now we've got the incoming current, incoming probability, and we can compute the differential cross section, right? So the differential cross section is just the rate divided by that current, and if I plug in those expressions that I just calculated, I end up with something that looks like this, right? But V is going to be a function of spatial coordinates, right? And what we have are matrix elements. Because we've chosen to work in momentum space, we have this matrix element of V inside, we have to evaluate momentum space. So what we want to do is insert some complete set of states, position states, because then we'll be able to evaluate this momentum operator because it's just a function of spatial coordinates, right? Position coordinates. So that's what I'm going to do. I'm going to plug in 2 factors of 1 on both sides of V. And then I'm going to use the fact that when this R hits this P, it's going to give me a plane wave, right? So one plane wave would be outgoing and the other one would be incoming, right? And so let's see what we have. So here, I've plugged in my 2 factors of 1, right? And now this guy, again, we're assuming that this thing is diagonal in position space, right? So this thing's just going to give me V of R prime times the delta function that comes from the overlap of R prime and R double prime. And then we'll have 2 factors of this plane wave, right? And if we group everything together and we can define this new quantity, this new vector called Q, and Q is nothing but what it is what we call the momentum transfer, right? It's because it's the momentum, it's the difference between the final momentum and the initial momentum. Okay, and that's just introduced there for to make it more concise. We can actually compute this thing, and it comes in handy. So I'll go ahead and do it. So we can compute the momentum transfer, and the way you do it is you consider the momentum transferred squared, okay, because it's a scalar. And so if you compute this thing, if you dot all this stuff out, you get PF squared plus PI squared, and then the cross term, right? And so PI, we know it lies all in the beam axis, right? So it's all in this direction. So it's going down the Z axis. PF is along this direction, right? And we're assuming that they both have the same magnitude. Where are we? Okay, so we're assuming they have the same magnitude, and that magnitude is just h bar squared k squared, right? Whatever k is. And the dot product of these two is given in terms of that angle, right? The angle that we were just talking about, right? So you can write down that dot product. And so you can factor some stuff. You can factor the 2 h bar squared k squared out. H bar squared cancels this h bar squared. And we end up with something that looks like 2k squared times 1 minus cosine theta for the momentum transfer squared. And then you can use, if you want to be fancy, you can use one of your trig identities and rewrite this factor of 1 minus cosine theta in terms of a sine squared of the half angle. Okay. But the important point is that if you look at this expression for the cross section, you see that all the dependence on the energy, the initial energy, and the angular dependence is all locked up inside of this momentum transfer, right? You can see it here, right? So that this factor of k squared is related to our energy squared, and this factor here, or right, yeah, and this factor here is takes up all the angular dependence, right? So it tells us that if I could take the square root of this just to get the magnitude of the momentum transfer. Okay, and so finally, if we take this expression here, right, for our cross section, and we compare it to the general expression, which I had back here, right, we can read off what the scattering amplitude is, right? And if I go back and I match those two, I find that the scattering amplitude is just this piece, right? Because it's getting up here, we have modulus squared. And if I get all the factors right, when I'm matching, I find that the scattering amplitude looks like this, okay? And this is known as the Born approximation, right? It's a Born approximation because we've only computed this thing to lowest order, okay? So when you hear Born approximation, always think lowest order. Okay, and one thing that you notice is that, if you forget about these factors here, you notice that the scattering amplitude is basically just a Fourier transform of the scattering potential, which is interesting in its own right. Yeah, so the last thing we're going to do is that, is to consider that we're only going to be dealing with spherical potentials, right? So all the what am I trying to say? The angular dependence is not going to be anything more than what's in the exponential. So it means that we can go ahead and perform or compute the angular integral that's in this integral, right, for the scattering amplitude. And so that's what I did. So if you take that dot product between Q and R prime, you get something that depends on the angle, and that's the only angular dependence. And so I can do not only the phi integral, but I can also do the theta integral. And so what we end up with is something that looks like this, right, where we've integrated out all the angular dependence, or you could integrate out all the angular dependence, right? And that thing, typically we just write it as f of theta, right? So a lot of times in books, you'll just see this notation, and it's because azimuthal symmetry, there's no dependence on the azimuthal angle, right? And so it's always just the theta dependence. Okay, so that's where I want to stop for today. And then next time we pick it up, we'll use our Born approximation and plug in some scattering potentials and see what we get for cross sections, right? And we're going to start with the Yukawa potential. Okay, so I can't think of anything else to say, so I'll just say goodbye, and I'll see you on Wednesday.